Right. While journeying through hosts of problems and concepts in collisions, I came across this interesting situation which I want to share with you. What we have is a string of length L, light inextensible string of length L, and there is a mass M2 300 grams attached at one end of the string. And there is another string which is sagging and is also length L. You know, this is the sag, a sagging string of length L, and with a mass M1 or 100 grams attached at this end P of the string, right? Now, everything is at rest. And this distance between A and P is given to be root 3 by 2 L. L is the length of the string. And this also is L. This also is length. Now, P is, this mass M is released from this point. Now, when this mass at this point is released from this end, what's the tension in a sagging string? The tension in a sagging string is 0. It's as if the string doesn't even exist, right? That's the tension. So then, what's the only force that M1 experiences? Downwards, gravity. And that will be the only force that it will experience till such time that there is tension developed in the string. Till such time that the string becomes taut. But till the time the string remains sagged, right? It's going to be experiencing only gravity, and it's therefore going to fall vertically downwards. Now, while this falls vertically downwards, the mass M1 falls vertically downwards, the sag, the slackening of the string will decrease, right? The string will slowly and gradually start to restore its original length, right? So the sag decreases, it falls a certain distance, when the particle goes from P to Q, right? The sag vanishes. The string acquires its actual length L, A to P. This distance between the particle and the string is the string length L. That's when tension starts to develop in the string, right? When the string acquires its actual length, the sag vanishes. So then, in its journey from P to Q, what has happened? It has only fallen vertically downwards. And by the time it falls vertically downwards, the string makes an angle theta with the vertical, right? This string, A to P, right? It falls to a point Q. It makes an angle theta with the vertical. This length, as you can see, is root 3 by 2L. This length is L. If this is theta, alternate angles, this will be theta. Very clearly, ordinary geometry, sine theta therefore is going to be what? Sine theta is going to be root 3L by 2 divided by L. Root 3L by 2 divided by L, which is root 3 by 2, causing theta to be 60 degrees. Causing theta to be 60 degrees. Yes or no? Theta is therefore 60 degrees. So, the string becomes taut. The string becomes taut at this point when this angle becomes 60 degrees. Now, till this point, there was only gravity that was at play. From this point onwards, from Q onwards, the string tightens, it loses its slag, it loses its slackening, it now becomes taut. The string has become taut, and therefore, from this point onwards, there is build-up of tension in the string. There is build-up of tension in the string. So, by the time the particle goes from P to Q, do you realize it has acquired a downward velocity V0? It has acquired a downward velocity V0, and it has fallen through a length, which is what? L. This is L. So this length is L cos theta. That's the length through which it has fallen, L cos theta. And if PQ is L cos theta, then the velocity acquired V0 in falling through this length, the velocity acquired in falling through this length is root 2g into the height through which it falls, L by 2. Yes or no? So, which is like root GL. So, it acquires a velocity root GL at an instant when the string becomes taut again. So, this is V0. This V0, which is root GL. Now, this velocity could have been resolved as V0 cos theta along the string, right? Along the string, and V0 sin theta tangential, perpendicular to the string. From this point onwards, the mass M1 will take to a circular trajectory, of radius L. Circular trajectory of radius L. Yes or no? Now, what happens at this instant? What happens at this instant? There is impulse of tension in the string J. And what does this J do? it kills this velocity v naught cos theta, right? The particle m1 can't have a velocity in this direction because the string is inextensible. And what therefore kills the velocity in this direction, that is the v naught cos theta? You know, this v naught cos theta is killed by something. What? What or who kills this? The impulse of tension J, built up when the string just about becomes taut. So v naught cos theta vanishes. So that means from this point onwards, it's v naught sine theta purely a tangential component. There will be no component of the velocity along the string because impulse of the tension will kill it. Now, Q2S is a circular trajectory of radius L, center at A, right? So, this Q2S, this journey from Q to S, it starts from Q with v naught sine theta. Why? Because v naught cos theta has gone into oblivion. It has vanished because the impulse of tension killed it completely. Now, by the time this m1 comes to the point S, this point S, it acquires a velocity u1. And between this instant and this instant, I'll apply conservation of energy. From this to this, what has happened? It had kinetic energy half m1 v naught sine theta whole square. This is v naught, this is sine theta whole square, right? That's the kinetic energy it has. What's the potential energy it has at this point compared to this point? Mg into this length. Mg, m1g into what is this length? This length, as you can see, is L minus L cos theta, which is this length. So this quantity, m1g L into 1 minus cos theta. So that's the total energy at this point, kinetic plus potential. When it comes down here, this is 0 of potential energy. So it has purely kinetic half m1 u1 square, right? So we can compute the velocity of m1 when it reaches this bottom. And that turns out to be, as you can, if you calculate, if you plug in values here, theta equal to 60 degrees, root GL, everything known to us, then you will end up getting u1 equal to 4 meters per second. Now what happens? This m1 at the bottommost point at S is moving horizontally with a velocity u1 and m2 is at rest. This m2 is at rest. Just before collision, m1 hits m2 horizontally with a velocity u1 and m2 is at rest at S. This is at S. m2 is at S. This is how collision occurs. And post collision, just after collision, JAC, just after collision, their velocities will change. m1 acquires a velocity v1, m2 acquires a velocity v2. And between just before collision and just after collision, I'll conserve linear momentum horizontally. So can I say m1 u1, total initial horizontal linear momentum is going to be m1 v1 plus m2 v2. This is conservation of linear momentum, yes or no, right? Also, the fact that the collision is perfectly elastic is characterized by this. What is E? E is v2 minus v1 relative velocity of separation, v2 minus v1 divided by u1 minus 0, and that's given to be 1. That's given to be 1. Now we have condition for linear momentum, condition for collision being perfectly elastic. From these two, if I solve for v2, from these two, see, because u1 is known to me, the two unknowns are v1 and v2, I'm interested in velocity of m2 after collision. v2. So if you end up solving these two, you'll get v2 equal to 2 meters per second, out of solving equations 1 and 2. Equation 1 is about conservation of linear momentum. Equation 2 is about the collision being perfectly elastic. v2 is 2 meters per second. So now look at m2. m2 is moving leftwards with a velocity v2, right? It's tied with a string, and eventually it'll keep rising. It'll keep gaining potential energy, and there'll be a point when all its potential energy, all its kinetic energy, half m2 v2 squared, gets converted into potential energy. It would be at rest, and that would be the highest point above the ground it's going to attain, right? So half m2 v2 squared would be converted into potential energy mg h max at the highest point. And when you solve for h max, you get h max is v2 squared by 2g, which turns out to be 0.2 meters. So it's not a difficult situation, but I think a relevant situation, and I hope you would have learned a few things out of this. Thank you so much.